Alright guys, welcome to your very first video lecture. I guess it's a lecture. Today we're going to be talking about relationships between variables in science. And for this class, all you guys need to worry about are three types of relationships. And you probably have heard of these before in your math class, but I want to go over them and talk about how to recognize these three kinds of relationships when you see them in data that you gather in a lab. Alright, so let's look at the first one. And to do that, we're going to think about a research question. So let's say I want to know, does eating lots of pizza make you fat? Okay, so that's my research question. And let's say I went out and did an experiment and gathered a bunch of data, and I plotted that on a graph. Okay, now in science we almost always use scatter plots when we're analyzing data. And if you don't remember what a scatter plot looks like, there's always the x and the y-axis. So this is the y-axis vertical, and the x-axis is horizontal. We always plot the independent variable, the one that we manipulate as the experimenter, on the x-axis. Okay, so this is the independent variable. That's on the x-axis. And then the dependent variable, which is the thing that we measure, goes on the y-axis. So this is the dependent variable, goes on the y. Okay, so remember, independent is what we manipulate, and it goes on the x-axis. Dependent is what we measure, and it goes on the y. Now, our question again was, does eating lots of pizza make you fat? Okay, so in that research, in that question, what do you think the independent variable would be? What can we manipulate to answer that question? I want you to think about it for a second. So you should have identified the amount of pizza that you eat is what we can manipulate. Okay, we can't directly control how fat someone gets, but we can directly control how much pizza somebody eats. So the amount of pizza is going to be our independent variable, and the fatness, we'd have to have some way of measuring that, maybe with body mass index or percentage of body fat or something like that, would be what we measure, and that would go on the y-axis. So let's say we did the experiment. Okay, and what the data would probably look like is that when we eat a certain amount of pizza, we get a certain amount of fatness. Okay. And when we eat more pizza, well, you probably get a little bit fatter, right? And if you eat even more pizza, you get even fatter, and then it keeps looking like this. Okay, so what we see here is that there's a relationship between the amount of pizza that we ate and how fat we got. In fact, what we see is that the more pizza you eat, the fatter you get. You can see that as this variable goes up, which is this way on the x-axis, the other variable also goes up, which is up on the y-axis. And so the relationship between the independent variable and the dependent variable for this particular experiment is what we call a direct relationship. Okay, and the key thing I want you guys to be able to recognize is that for a direct relationship, the graph ends up looking like a straight line. Okay, if we connect these dots, we get a straight line graph. Now you could also have a straight line graph that's going with negative slope as well. But the key thing here is the shape of the line is straight. Okay, it's a straight line. That's called a direct relationship. All right, so there's other kinds of relationships you might see in science. So let's say you graph your data from a different question. Again, y-axis, dependent variable, it's what you measure. X-axis, independent variable, it's what we manipulate. And let's say, in this case, your data ends up looking like this. Okay, it starts off kind of looking like a direct relationship, but then, oh my goodness, it just goes crazy over here, right? It just takes off and shoots off up into the stratosphere. So this relationship is much different from the direct relationship. This kind of relationship, where one variable increases a little bit and the other variable increases a lot, like a crazy amount, is called an exponential relationship. And these are really important in science because they behave a lot differently than a linear relationship. You can see, if I change this x-axis, this x variable, by just a tiny bit, I'm going to get a huge change in y. And that has all kinds of interesting effects in science, and we'll see some of those later on this year. In fact, you guys will see one of those coming up here later this week. Okay, so the third and final kind of relationship you guys need to worry about or think about this year is one that ends up looking like this. So again, y-axis, x-axis. What if your data ends up looking like this? Okay. Now this one's different, okay? Look at the graph. As x increases, we move this way, right? Think about what's happening to y. We can see that the bigger x gets, the smaller y gets. Y starts off way up here when x is very small. But when x grows to the right here, y gets smaller and smaller and smaller, and it approaches 0. It never quite gets to 0, but it approaches 0. You guys will learn about that in pre-cal. So this is a different shape than the first two we've looked at. It has very, very different characteristics in the real world. Okay? This kind of relationship is called an inverse relationship. Okay? All right. So just to review real quick, we've had three kinds of relationships so far. First kind, when the independent variable increases, the dependent variable changes at the same rate. Okay, so usually either goes up or down, but it's always a straight line. Okay, this is called a direct relationship. You can also have a kind where, again, this, when the independent variable changes a little bit, the dependent variable changes a lot. Okay, so it has a different shape. It swoops up like this. Okay, it shoots up into infinity. This is called an exponential relationship. And then finally, much different shape than these other two, you have y starts off very large when x is very small, but then as x gets bigger, y gets smaller. This is called an inverse type of relationship. Okay, so those are your three: direct, exponential, and inverse. All right, so those, I want you to be able to recognize those three shapes of graph, because in science, when you do an experiment and you plot your data, it'll almost always be one of these three types of relationships that you see in the data, and that those types of relationships mean something important. Okay, now, because chemistry is a quantitative science, and because scientists communicate with each other using math, you also need to know what these types of relationships look like in their mathematical representations. So don't freak out, okay? It's not scary. I just want you to look at this real quick. Let's say I have this equation, y equals x, okay? As x gets bigger, what happens to y according to this equation? Think about it. If x is 2, what does y have to be? Well, y has to be 2, right? If x goes up to 3, y also has to go up to 3 as well, because in order to keep these equal to each other, right? So when x increases, according to this equation, y also increases, right? What kind of relationship does that sound like to you guys? Think about it. Yes, that is correct. It is a direct relationship, all right, with a positive slope in this case. So as x gets bigger, y also gets bigger. So this is a direct relationship. Right? Now, all equations that have this general form have a direct relationship between y and x. What do I mean by general form? Okay, so let's look at this equation. What if we had y equals 4x plus 2? Okay, this equation looks a little bit different from that equation, but they have the same general form. And what I mean by that is look at the positions of y and x relative to each other, okay, across that equal sign. Y and x are straight across from each other across that equal sign. This 4 and this plus 2 don't change the relationship, okay? The only thing that matters here is y's relationship to x, okay? So this equation and y equals 4.927 plus 3x, this equation, this one, and this one, all three of these have the same relationship between y and x. Again, just focus on the y and x, block out all the other numbers, and you'll see y and x are in the same positions in all of these equations relative to each other, I don't care about the other numbers, right? So in order to kind of simplify this whole thing, we'll say that any equation that looks kind of like this is a direct relationship. So how do we represent that? Well, instead of having an equal sign, we put in a different thing called a proportionality. It looks like a fish. So what you might see me write is y is proportional to x. Okay. This just means that y is not necessarily equal to x. It just means that when x goes up, y also goes up. So this is the form of the relationship for a direct relationship. It looks like this when you write it mathematically. Y is proportional to x. In other words, when y goes up, x goes up. When x goes up, y goes up. When x goes down, y goes down. That's true for all of these equations. And that's always true for a direct relationship. Okay, so that's the mathematical form for a direct relationship. Let's look at an exponential relationship. Okay, so remember that's the one where you have a little change in x makes a big change in y. Okay, so it's going to go up like that. Crazy. All right, so you may have guessed already what this one's going to look like, but y is going to be equal to x squared. Okay, so what this means is, if let's say x is 2, according to this equation, y is 4. All right, but then if we increase x to 3, y doesn't just go up to 5 or 6. When x is 3, y is 9. Okay, that's a huge change. When x becomes 4, y becomes 16. Right? When x is 5, y is 25. You can see that the difference, the increase, is going up like crazy. As x gets bigger, y gets bigger as well, but it gets bigger by a whole lot, right? And that's what this equation shows us, okay? So for an exponential relationship, all the equations look like this. They look like y on one side and x raised to some exponent on the other side. So this is one specific kind of equation, but the general relationship is represented like this. Y is proportional to x raised to some exponent. We don't care. Any exponent we want, right? So this could be y equals x cubed, y equals x to the 5th. It doesn't matter. The point is that y and x are across from each other now, but this time x is raised to some exponent. And that makes x, small changes in x lead to very, very large changes in y. All right? So that's different from the linear relationship, because in the linear relationship, it was just y straight across from x. This time it's y straight across from x, but x is raised to some power. And so small changes in y lead to big changes in x. The last kind of relationship that we talked about before was an inverse relationship. Just think about that word inverse, right? What does inverse mean? And what did the graph look like? Okay, so on the inverse relationship graph, as x got bigger, what happened to y? Y gets smaller. Right? So large x, the larger x is, the smaller y is. So how can we represent that with an equation? How can we represent that with mathematical symbols? Okay, instead of writing that out in a big old sentence every time we want to express this, that's why math was invented, so we could have symbols that express these ideas. Okay, so as x gets big, y gets small. What has behavior like that? Well, a fraction does, right? Think about it. The bigger the bottom of a fraction is, the denominator of a fraction is, the smaller that fraction's value is, right? So if I want an inverse relationship, it looks like this. Y is proportional to 1 over x, right? So you look at this expression here. When x is very, very large, this fraction equals something very small. Okay, so large x leads to small y. That's an inverse relationship. It's opposite of the other ones. So the last thing to review here is the mathematical expressions for these three relationships. So we have a direct relationship, which always looks like y is proportional to x, and they're straight across from each other. You can have an exponential relationship, which looks like y is proportional to x raised to some exponent. Doesn't matter what the n is. And finally, you can have an inverse relationship, which looks like y is proportional to 1 over x. Okay? These three kinds of relationships show up over and over and over in scientific laws, and you're going to see them a lot this year in the lab in your data. So it's important that you guys can look at an equation and tell me what kind of relationship there is. So let me give you one quick example of something cool that you have probably seen before. So this is probably the most famous equation in all of science. You guys have definitely seen it before. E equals mc squared. Okay, this is Einstein's equation from general relativity. And it's really famous because it's what kind of led to, you know, the discovery of nuclear bombs and all this cool stuff. Not that nuclear bombs are cool, but the theory behind them is interesting scientifically. So what we can see in this is that there are three symbols in this equation. This is energy. E is energy. M is mass. And c over here is the speed of light. Now, why does energy equals mass times the speed of light? Why is the speed of light in there? Why does that even make sense? That's really interesting stuff, and that's relativity, and we're not going to talk about it this year. But if you're interested, you should look up relativity and teach yourself about why the speed of light's in. It's really, really cool stuff. But we have energy equals mass times the speed of light squared. The speed of light is a constant. It's just a number that never changes. So I want to look at the relationship between energy and mass. What kind of relationship is that? What does it look like to you guys? Which one of the three that I showed you before does Einstein's equation match up with the best? Now, some of you guys might be tempted to say exponential, okay, because there's an exponent here. But I wanted to know what is the relationship between energy and mass. I don't care about the speed of light, okay? I just want to look at these two. And you can see here that the relationship between energy and mass is direct. So that tells us in the real world, this equation tells us the more mass something has, the more energy it contains, because there's a direct relationship between mass and energy. And that is actually a pretty cool thing. And in fact, something else that's interesting here is that the more energy something has, the more mass it can also have, which is another interesting thing that comes out in science. So, if you can recognize these types of relationships in mathematical equations, if you can train yourself to look for the type of relationship between the two variables, then you can actually learn a lot about what's going on in an equation without having to solve it at all. If you just look at where one variable is in relationship to the other one, it can tell you a lot about the behavior of what that equation is describing. And I know it's maybe all a little bit hard for you guys to grasp right now, but you will later on this year. So for right now, focus on those three kinds of relationships: direct, exponential, and inverse. Be able to identify the type of graph and also be able to identify the mathematical equations. All right, great job, guys.